Hi everybody, welcome to test 3 review for differential equation. As always, the list of the problem that we've done will be on the top, and on that side will be the table of Laplace transform for this time. Right, now let's just go over this problem. So first, from 1 to 7, we find the Laplace transform for some function. So let's look at the first one. So first, Laplace transform, just like derivative or integral, is a linear operator, which means we can split. And then just look for t square. Transform of t square will be 2 factorial over s cubed, and then in the Laplace transform of 1 is 1 over s. So pretty much we have 2 over s cubed minus 5 over s. Right, let's me up. Yeah, let me update the list. Right. Right. Next on this one, where we have e to, in this case 4t or whatever the power is, that will be the translation in s. So we ignore that, the e. Let me just write that out again. T e to the 4t now for this exponential part of the function will result in the transform of just t. So pretty much we ignore that, and after the transform, s will become s minus 4. So we will have transform of t is 1 over s squared. Now instead of s, we have s minus 4, so 1 over s minus 4 squared. Right, so that's some transform. Right, 3 straightforward. The table Laplace transform over there, so just look up for that. Yeah. So we have cosine, pretty much this, and then e to the t, that also a transform. Either we use that, or we use these properties, or we use the transform like we just did. I'm more interested in doing number 5 instead. So number 5, we have cosine of t, but this time we have t in front of it instead of e to the t. So this is not the transformation, but rather it is the derivative of a transform. Oops. Should be this. Right. So number 5. So transform of t cosine t. Now this is to the first power. So in that formula, this is because of the first power, we'll have -1. This is by default is the first power, so we have the first power here of -1. And then we do the transform of t, cosine t. But then we have to take derivative of that. This is the first power, and we will take the first derivative. So the power of t, the power of -1, and the order of derivative, all of that will be the same. Right. So it will be negative. Transform of cosine t is s over s squared plus 1 square, or just plus 1. Now we just take derivative. This is the quotient rule, so we have 1 s squared plus 1 minus s, derivative of the bottom is 2s, and the bottom square. Right. The top we have s squared plus 1 minus 2s squared. The bottom is s squared plus 1, all that square. Put everything together. On the top is minus s squared, but with another negative sign. That will be s squared plus 1 with a negative becomes -1. So we do that. So pretty much when we have the t in front of the function, that is the derivative. The power of t will be the power of -1, and the order of derivative, all of which must be the same. So that is number 5. Next, I'll be number 7. And in class, I did mention that we have to change the problem to a plus. Right. Now there's a unit step size function, so the transform of that is going to be here. Right. So first, I just rewrite the problem with the Laplace transform. Right. Now in the formula that I highlighted, we need to have the g of t, so this will be g of t. And from here, a is going to be 2. Right. Next, we need to find the function of g of t plus a, or t plus 2 in this case. So g of t plus 2 is, I'm going to put t plus 2 into t. So e of 2 plus t plus 2. So e of t plus 4. Right. So that is the function of g of t plus 2. Now the transform. So according to that formula, when we have the u, the step function, that will become e to the negative as. A in this case is 2, so e to the negative 2s. And then when we have a transform of the function g of t plus 2, so have e to the negative 2s, the transform of e to the t plus 4. Right. Notice that we don't see the t plus 4 in here in the transformation, but we can just simply do e to the negative 2s Laplace transform e to the t times e to the 4, where e to the 4 is just a constant. Now we can take it outside. I'll just have the transform of e to the t, which will be 1 over s minus 1. Let's go back to the default. So we have those two terms on the top. S minus 1. Yeah, so e to the t, 1 over s minus 1, and then those terms. Right. Yeah, the answer is different than the key, obviously, because we change the problem to a plus. So that was 7. So transform with the unit step function, that will be e to the negative as, and then we transform g of t plus a, and g of t plus a is this, and we transform, and that's what we have. Right. Now to the switch. Right. In this case, we will write the function as the sum of the Windows function. So we have x squared, the Windows function will go from 0 to 2, and 3x times the window function that goes from 2 to 3, and then plus 1. It's not the window function because that's for x greater than 3, so we write u of x minus 3. It should be t because usually this is a function of t, but it doesn't matter. Right, so I have x squared. The window function is simple. It's just the unit step function of x minus the first one, and then another one, x minus the next values, and then the same thing for the other window. This Windows function, u x minus 2 minus u x minus 3, and this is plus u x minus 3. Right. Now, because we really don't care what happened for the function that is less than 0, so we pretty much just let this equal to 1. That is, assume that we don't care what happened when x less than 0. And also not to mention that we really don't need to have the equal sign in the transform. I mean, not the transform, but the piecewise function. Equal or not doesn't matter. Anyway, so that is 1. So you have x squared minus x squared u to the x minus 2 plus 3x u to the x minus 2 minus 3x u x minus 3 plus u to the x minus 3. So we have x squared minus, both of these have u to the x minus 2. I'll factor it out, but let's just write like this. And then those two have x minus 3. I'll factor it out. Now, let's consider this. Originally, we have x squared. When we have up to 2, the x squared minus x squared will cancel out. Now we'll have 3x. Now the 3x will go until 3. The 3x will cancel with 3x. So from 3 on, we're going to have 1. So that looks right. Once again, original is x squared. After that, when passing x equal to 2, the x squared minus x squared gone. We only have 3x left. Now the 3x will continue up to 3, because when 3, the 3x minus 3x, we only have 1 left. And that is the piecewise function rewritten in terms of unit step function. Right. Because number 8 will be similar to that. Right. Next we do the inverse transform. Inverse transform is just pretty much just like the transform, except we have to read on the table backward instead of left to right for the transform, from right to left for the inverse transform. Right. Let's look at 11. Alright, if you look at 11, it is unlike any form we have. So we have to rewrite this a little bit. So if we have to factor out the 2, so we have s minus 1 half right. Now we multiply it out, factor out the 1 half. We have 1 over s minus 1 half. Now we do the transform. Will be transform of this. Right. So we have 1 half. This will be e to the 1 half s. I think that, sorry, that should be t. We'll go back to t. And that is the inverse transform. Sorry. Yeah. So inverse transform will go from S to T, and that is that, of course, pretty much the highlighted, I mean, the highlighted formula. So yeah, as long as we have the right form, we will find the inverse transform just like that, right? So that was 11. Right. Next I want to look at 13. I haven't done that yet. Alright, 13. Once again, we rewrite the function. This we cannot factor, but we can make a complete square. So we have x plus 2 square plus 1. Notice that if we cannot factor, we cannot do the partial fraction because the fraction that already reduced. What we do is we need to manufacture the x plus 2 similar on the top. So we'll do the 3. We're going to need the plus 2. So let's do this. Plus 2. Now, that means 3 plus 2 is 6, so we plus 6 to the problem. We have to minus 6 to keep things balanced. And then we still have minus 7. So that would be 3s plus 2 minus 13 s plus 2 square plus 1. Right. Now we do the inverse transform of this, which is that, pretty much the same. So inverse transform of 3s minus 7. Right. Will be transform of that. Right. Now we split in 2. One you can write like 1 square, and then just say minus as pull out the 13. So I have that. Now the inverse transform of this is going to be, by this I mean this part. The constant in front doesn't really matter. We can just write 3 in front of it. Now the s plus 2 is that. If we looked down here, those are the transformation. So this will be e to the negative 2s 2t, sorry, cosine of 1t, and that is minus 13 e to the negative 2t sine of b is 1, so sine of t, so pretty much that. Right. Right. So that was 13. Now we go to 15. Right. 13 we have e to the negative as. Pretty much this. So 15. Inverse transform. First we see the e to the negative pi s. That is the unit step function of u t minus pi. And we'll take that away. Now we just have the transform, the inverse transform of 1 over s squared plus 1. Notice that is not it, because e to the negative pi s, that is the translation in t. So instead of t, we have to replace t by t minus pi, exactly like this. Because bottom line is, when the transform, we see that the function we have t minus a, and the unit step function also t minus 8. So the variable must be the same. So the transform of inverse transform of 1 over s squared plus 1. I just have the unit function first. That will be just sine of t, but now t becomes t minus pi. So put t minus pi in, and we usually write whatever the function is in front, and then the unit step function on the back. Right. So that's what we have. So the e to negative something s is the translation in t as this backward, or if e to the something t, that is the translation in s. Yeah. So that is u, the step side function t minus pi, and then t minus pi instead of t. Alright, so that was 15. Next we'll have some problem that we'll do using the Laplace transform. Right. Want to look at this one. So using the Laplace transform first, we take the derivative of the Laplace transform. Sorry, take the transform of the differential equation. So first, we take the Laplace transform. Laplace transform is linear operator, so just do that. Right. Now the transform of the second derivative is going to be s squared minus s that's fine, and then minus with no s. The y will transform into big Y of s, and then the initial condition y of 0, y prime of 0. So that is the Laplace transform of second derivative. I highlighted on that side. Right, next, transform of the function, that's just big Y of s, and transform of e to the negative t is 1 over s plus 1. Whole thing here, the values of the function is 0, derivative also 0, so it turned out to be pretty simple. And both of this, we see y of s, so we can factor it out. So the first step is take Laplace transform. The next step is solve for y of s. So both of them have y of s. We factor it out, and we have s squared plus 1. Right. Next, divide by s squared plus 1. We have y of s. S squared plus 1, and then s plus 1. So we done with this step. However, this is a factor, so more likely we're going to do the partial fraction. So now the partial fraction, we have 1 over s squared plus 1, and then s plus 1. The fraction we have s squared plus 1. This is the second order, so the second power, the top we have 1 less, and then the other one we just have s plus 1. So let's see, the power will be 1 less than the bottom. Right, multiply both sides by the common denominator, so we multiply this s squared plus 1, s plus 1. Right, and we'll continue over here. So we have 1 equal to as plus b times s plus 1 plus c s squared plus 1. Right, multiply this, the s plus 1 cancel out, and we have that. And multiply this into this, s squared plus 1 cancel out, we have s plus 1. Now we just multiply it out. As squared plus as plus bs plus b plus cs squared plus 1. Now we just do the combined like terms. This, the s squared, so we have a plus c s squared. This have s, so and then because we have b plus 1. So it's not plus 1, it's plus c, sorry, b plus c. Now we match that with the polynomial on the left, which is just 1. So we will have the system of equation. A plus c is equal to 0, a plus b is equal to 0 as well, and b plus c is equal to 1. Right. I'm using the calculator on this one. Application. Look for the system of equation. Right there. Simultaneous equation solver. 3 variable, 3 unknown. Right. Coefficient A is 1, 0, 1, 0, 1, 1, 0, 0, 0, 1, 1, 1. So A is negative 1/2, B and C 1/2 and 1/2. Right. Now we put it back into the function. So we have y of s equal to negative 1/2 s plus b. B is 1/2 over s squared plus 1 plus c is also 1/2 over s plus 1. Right. Now we have the function. Of course, we can split it like this: negative 1/2 s over s squared plus 1 plus 1/2 1 over s squared plus 1 plus 1/2 1 over s plus 1. I will just take the inverse transform. And we will have inverse transform of y of s. So we use a curly bracket. Negative 1/2 inverse of s squared plus 1 plus 1/2 inverse transform 1 over s squared plus 1 plus 1/2 inverse 1 s plus 1. Sorry, can't pronounce space. But pretty much just the inverse transform of each one. And we end up with negative 1/2. That is cosine of t 1/2. That is sine of t, and 1/2 e of negative t. Right. So that is 17. So pretty much take the Laplace transform, solve for it, solve for the y of s, and usually we have partial fraction after that. So we split y of s into a little fractions, so we can take the inverse transform. The transform always in the fraction form, so inverse transform we have to have for the fraction, and that's what we have. Right, so that was 17. Right. Right. Next we have the series 18. I will not ask you this kind of question about the convergence of the series on the test, so I'm not going to do that here. Right. Look at 20 instead. So in Taylor series in general, I will put this formula on the chart on the test, but it will be f of x approximately equal to a series this is centered at a, so we have a So we have the n derivative of a over n factorial and then x minus a to the n power. So there will be three components: the derivative, the factorial, and the power, all of which has the order of n, factorial of n, and n derivative. Right. Now usually I'll make a table from this. It will be as follows. Order 3, so we're going to go up to 3. So let's say n or j, whatever the index is, 1, 0, 1, 2, 3. Now we have the derivative of x. Then we do the derivative at a. In this case, a is equal to 5. And next we will have the term, the n derivative of that point over the same factorial. Right. Now we do that. The function is ln of x. We take derivative 1 over x. Derivative again negative 1 over x squared. Derivative again, that will be positive 2. Negative 2. 1 over x cubed. So I like 2 over x cubed. Right. Now put 5 in it, so it will be just ln of 5. 1/5. Negative 1 over 25. And 2 over 125. So the derivatives start from the function and derivatives, and then evaluate, put the numbers in x. And now we just divide by the factorial. So ln of 5 divided by 0 factorial. So it will be just ln of 5. 1/5 divided by 1 factorial. So it's still 1/5. Negative 1 over 25 divided by 2 factorial, which is 2. So we have negative 1 over 50. And finally 2 over 125 divided by 3 factorial. The 2 and 6, let's just write that. 2 over 125 times 6. The 6 and the 2 cancel out, so it's just 1 over 125 times 3, so 375. Right. And finally, the series. Let's set the order 3, so we say p of 3 of x equal to the first term and then we have x minus a is 5, the first one to the 0 power, pretty much that, go to 1. And then next we have 1/5, and then x minus 5 to the first power, and then 1 over 50. I'm sorry, not 1 over 50. That is 1 over 50, sorry. X minus 5 square, and then plus 1 over 375 x minus 5 cube. Of course that go to 1. So we have that series. So that is 20. So once again, the function and all derivatives evaluate at the point and then divide by the factorial. And after that, we have derivative over factorial times the power of x minus a to the n power. So we just have this. Right, that was 20. Next, we write the series solution for the initial variable problem. Right now we don't write using the power series to do that. First we're going to do using the Taylor series. So once again, the Taylor series. I'll do 22. So usually the y is a function of x. This time x is a function of t. So I will write x of t approximately equal to the summation of n go from 0 to infinity, the derivative, since we know 0, so derivative at 0 over n factorial, and then x minus 0 to the n, so n power n factorial and n order of derivative. If we write out, it will be like this: the function at 0, the derivative at 0 times x plus the second derivative over 2 factorial x squared plus the third derivative at 0 with 3 cube factorial x cubed, and fourth 4 factorial x fourth, and so on. I'm not sure how far do we need on this, but the question wants us to find the first 3 non-zero terms. Right, so let's see what we have. We know x of 0 equal to 1, so that is the first term, that is non-zero, which is good. Next, derivative is going to be 0. That is not good because this term go to 0. So we need to find something that is not 0. Right, anyway. Now, I'll go back to this problem. We have the second derivative plus tx equal to 0. We actually can roll around. We say second derivative equal to negative x times t. That might be a problem. Anyway, and now if we take the third derivative, we have to take derivative using the product rule. So going to be negative derivative x times t plus negative x times derivative of t, which is 1. Right? So negative derivative of the first with the second with a minus the first with derivative of the second, so just x. So pretty much just that. Now we take the fourth derivative, will be derivative of this, another product rule will be negative second derivative times t. Actually, I'm just better to use this one, and then minus the first with derivative of the second, the first with derivative of the second, yes, and then minus derivative of that. Let's see how do we do so far. We know that from here x will be equal to 1, x of 0 equal to 1, t equal to 0, and derivative equal to 0. So we have here, let's put the values in. Negative x will be negative 1, t is 0, so that's still 0, so that doesn't help. This might be better. Negative derivative 0, t 0, so that one gone as well. But we have minus x, which is 1, so it's good. So it's minus 1. So this will be equal to right. Next up, when we have t will be equal to 0, x prime is 0, x prime is 0, so pretty much this is 0. Doesn't help. So we have that term is 1, this is negative 1. Looks like we have to keep going. Right. The fifth. Right. That will be the third derivative times t plus first with derivative of the second, both of them 0. This minus the second derivative minus second derivative, both of them 0. So we have t is 0, second derivative is 0. All of these are 0 pretty much. So even though this is supposed to be a minus, still 0. Right. A bunch of zeros. I expect the next one will not be. Right. From here, negative x to the fourth times t, negative x cubed times 1, negative x cubed, and after that all of them just x cubed. Actually, we should start combining those. Anyway, x cubed is negative 1, so we have t here, so this is going to be 0. We have 1, 2, 3, 4. Which is negative 1. So equal to 4. So that finally we will have first one, non-zero is 1. Next step is this, negative 1 over 3 factorial x cubed. Next is not 0, is 6. So it will be plus 4 over 6 factorial x to the 6. Right, a bit tedious. Not perfectly sure if that's correct, but of course that's how we do. We just take the derivative and then we recursively we find the values. Right. So how it works. I will not do 21, but the list just to see how the recursion work. So derivative is y squared. If we check the second derivative, it is the chain rule, so we have 2y y prime, and then third derivative, this is the product rule. Notice that y is a function of x. By the way, now just realize that this is supposed to be t and then t. Yeah. Originally too. This should be t. That was x is correct, but this is t squared, t cubed, and t to the 4th. Yeah. I shouldn't just change the variable like that. But anyway, so x is a function of t, so that would be t. And that should be this. Anyway, I add back to this. So derivative of the first, we still have that. Plus the first with derivative of the second. We'll just keep doing like that. All of them are product rule, just like all of this are product rule. Sorry, a bit sloppy here, but yeah, it should be t, and those x are correct and derivatives are correct with the power of t. Right, so that's 22. Now 23, 24. Now just combine this series into one. This very simple. We just need to make sure that the series must start at the same numbers. We don't, and the index must start at the same power. Obviously they're not. So we just need to check. The first thing we look at is we put 0 in here. It starts at x squared. So put 0 in for n. The series here's the series start at x squared. Put 2 in here. The series starts at x. 2 minus 1 is the first. So we have 1 start from x squared, 1 start from x. So in that case, we have to split this series into 2. Not into 2, but split the first term out. We know this one we start at x squared. Then if we put 2 in here for all the n, we have 2, c of 2, x of 2 minus 1 is 1. Of course, that's where we start. So we split this into a term and then a series. Now we start from 3. So we still start from 2. Ignore the 2. To do that, just one term, and then the series will continue from 3 onward. Everything else will stay the same. Now if you put 3 in here, that will be x squared will be the same starting index. Right, next. What we want next is we want both of this to the power of k, to the same power. So we match this and this must have the same power. So let's match that to x to the k power. Because of that, the k will be equal to n plus 2. Or n is equal to k minus 2. Same thing here. N minus 1 we match to k, and n will be k plus 1. Now we substitute this into this series. That term we just leave it by itself. So I put that in front, so we will not do anything. Alright, now the first series, instead of n, we use k minus 2 equal to 0 to infinity. C of n, that will be c of k minus 2. X of, now since we match that to x to the k, so that must be x to the k. So pretty simple. Next, this series, n will be k plus 1 equal to 0 to infinity. N will be k plus 1 Cn C of k plus 1, and because this we match to x to the k. K minus 2 equal to 0, so k is equal to 2. And k equal to minus 1. Sorry, this was 3. So this should be 2. And of course we're supposed to have the same thing here. And we do. Right, k plus 1 for n, c of k plus 1, and then x of k. Now the series, now we have the same index, start at the same point, the same power, so pretty much we can combine them, and so we factor out the x to the k. Oops, sorry. So pretty much first we have to know where the series starts. Whatever the series start at the lower power, we have to split on the lower power so that both of them will start at the same power. Because if they start the same power, when we match to the x to the k, the index will turn out to be the same. If we match the original problem to x to the k and they don't start the same point, we will not have the same index. So that's what we don't want to do. Right. So that was 24. Now we'll go to either 25 or 26. Right. Uh, 25 seems easier. Right. So let's look at 26. So this is the power series solution. So we start with, let y equal to the series 8n x to the n. We'll take derivative. Will be n an x to the n minus 1, because it's n minus 1, sorry, it should be 1, because we cannot have the x to the negative power, otherwise it could be undefined. Then we check the second derivative. That should be 2 now, and n minus 1 an xn minus 2. Now we substitute into that second derivative. Plus 3x times the first derivative, that plus 3 times original function. Right, now we have 3 series. First, let's multiply the 3x and the 3 inside. So we just have the summation. So usually it is easier to pay attention to just everything after the summation, because we easily lose track of anything in front of it. We have 3n a to the n. Now x times that, so the power will increase by 1, so we just have x to the n power. Right. Once again, I will check the n, the 3 inside, because it is easier to keep track the things and everything after the summation. Now let's see where those series start. Put 2 in here. This one starts at x to the 0 power. This one starts at x to the first, and this one at x to the 0 power as well. So we need to split the first term out of those two, so all of them we start x to the first. Even though we have the answer on the back, but kind of difficult to check. So anyway, so first thing we put 2 in here. We have 2 minus 1, a of 2, x of 0, so that kind of 1 equal to 1. Next, the series will go from 3 now, because we already did 2. Now we will be 3 going forward. The next series will be the same. We have to split this as well. Put 0 in here. We have 3 a of 0, x to the 0 power. Obviously it's just that. And then the summation that go from 1. So those two terms together, we have 2 times 1, so 2a2 plus 3a naught. I just 2 terms by itself. I just want to check real quick. look right. Right, next we have those three series. Let's just rewrite that for a moment. Oh, nice. Those two are the same. But not this. I mean, not the same, but we can combine right away. It's good. Right. Just need to make sure they're the same thing. Right. Next, we match all of this to x to the k. With that, we will have n minus 2 will be equal to k, or n equal to k plus 2. This is easy. We just let n equal to k, and then we don't need to do much. So 2a naught 2 plus 3a naught k plus 2 infinity k plus 2 in for n equal to 3, sorry, will be k plus 2, k plus 2 minus 1 is k plus 1, n is k plus 2, and x should have the x to the k power. Now these two are easy. We just replace n with k. Right. And put all of them together. This, by the way, k plus 2 equal to 3, so k is 1. So we have 2a2 3a naught plus the summation of k equal to 1 to infinity k plus 2 k plus 1 ak plus 2, and then we have 3k ak 3ak x to the k equal to 0. Now if this equal to 0, need to zoom out because this is such a long problem. Now if this equal to 0, meaning all of the coefficient must be 0. So we make this equal to 0 and all of this equal to 0. Right. So we have 2a2 plus 3a naught equal to 0. So from here we write a2 is negative 3 over 2a naught. That's what one coefficient. Now this. Even then I don't think we have enough space. Anyway, So we can factor out the 3 and ak, move to the other side, and we have k plus 1 over k plus 1, k plus 2. Actually, it's not bad. Now we have that. Now let's choose some values, and the values we choose is starting from k equal to 1. So k equal to 1, we put 1 in here, so it will be a of 3 equal negative 3, k equal to 1, so negative 3 a1 over 1 plus 2, so be negative a1. Check real quick. Look right. Now go to k equal to 2, put 2 in here and here. I just put this, so a3 negative a1. a4 equal to negative 3. If we put 2 in for k, 2 here, so that's 4, and 2 here, so a2, and 2 plus 2, negative 3 over 4, a naught, sorry, a2, and a2 is this, so negative 3 over 4 times negative 3 over 2, a naught, so will be 9 over 8, a naught, and that is 8, 4. Right. Now in terms of a0, we have a0, a2, and a4. So all three terms in terms of a0, which is good. We just need to have 3 terms of a1, and that would be good. Let me check real quick. Look right. I think one more will do. Negative 3, a3, 3 plus 2, negative 3 over 5, a3, a3 is negative a1, let me check real quick. Actually, I'm checking with the answer on the back and try to put k equal to into the summation and see if it is working. And So look right, and this is a to the fifth. Right. Now we write the answer. Y equal to a naught plus a1x plus a2x squared. This is the power series and not the Taylor series, so we don't have to divide by the factorial. A3x cubed, a4x4, a5 x5, and then so on. Now we put on the coefficient we have. We don't have a naught or a1, so it's still there. A2, we do know a2, negative 3 half a naught x squared. We do know a3, negative a1 x cubed. A4 is this, and a5 is this. Right, and then we can pull on the term that has a naught, 1, 2, and 3. So we need 3 non-zero terms. So that's exactly what we have. So it will be 1 minus 3 half x squared, assuming that may not be as bad, and then plus 9 over 8 x to the fourth, and then so on. And now I will have a1, we have x minus x cubed plus 3 over 5 x to the fifth. Sorry, can't run out of space, but we just factor out all the a naught and all the a1. So we have 3 terms for each constant, and that's exactly what the question wants us to do. So pretty much that is that. And the 25 will do the same thing, although it's less complicated. Right. So this y is the constant, and so this is what we have. Right, so that's the end of it. Yeah, so this problem with the series, usually we should write the answer in terms of the pattern. We see the pattern here look like 1, 3, 9. The next one should be 27, and then we have 2, 8. I'm not sure what's next, but we have to do a few more terms to see the pattern. We won't be able, we will not have enough time to do that on the test, but so that's why we only find 3 terms for each constant, and that would be it. And with that, we finished the review for the test, and I hope this helped you to prepare for the test on Monday. On Monday, as always, we start with a few questions, and the test will start at 8:30. Have a good weekend, and as always, thanks for watching.